engaged and everything on the move ahead. Any questions about where we left off at? Gabriel synthesis, including double hydrolysis of this imide. Okay? All right, if you don't know what a hydrolysis reaction is of a carbonyl compound, you need to figure it out. You need to ask questions. You need to read your textbook. Any questions? Okay, dehydration of primary amides to nitriles using thionyl-chloride. Primary amide, thionyl-chloride, we can get nitrile plus SO2 HCl. I gave you the mechanism here on the white sheet today. Okay? Please take a look. It's pretty consistent with other things we've been doing. And it's a nice reaction. Everything leads sort of downhill to give the nitrile compound plus SO2 plus HCl. We are removing H2O from the amide, so it is a dehydration. And we lose the carbonyl. The carbonyl is now gone. Okay? H2O. We end up with a triple bond between the C and the N. And we usually show the cyano group as condensed, CN. Chemistry of nitriles. Synthesis using cyanide, we've already seen that in Roman numeral 1C. And we just saw another synthesis, dehydration of a primary amide. So we just did that, 4C. Those are two common syntheses of nitrile compounds. B, hydrolysis back to carboxylic acids. Of course, every acid derivative can be hydrolyzed back to carboxylic acid. Okay? This can be done with either aqueous acid or aqueous base, as shown on the outline on the back of the first page of the green sheet. Okay, can you show hydrolysis? First we get the amide. Because if you go this way, it's a dehydration. We just showed that, right? Dehydration of amides to nitriles. But if you go the other way, it would be called a what? Hydration. Or you could call that a hydrolysis. Now, hydrolysis sounds like it's water breaking. Water lysis, water breaking. You're actually not breaking any bond, well, you're breaking pi bonds here, but you're not cleaving anything. Next, we cleave the CN bond, and so that's more specifically or correctly a hydrolysis, but we call this hydrolysis also. How's your textbook with acid derivative chemistry? It's pretty consistent with what I'm covering? Yeah? Okay, working problems in your textbook? Yeah? Any questions about problems in the textbook? Be happy to work problems in the textbook if you'd like. Okay, you want to show hydrolysis mechanism here? unless anybody already has it. Anybody already have hydrolysis mechanism shown out? Let's look at miscellaneous topics. All right. If you'd like to show me a hydrolysis mechanism, I'd be happy to look at it. Okay. Miscellaneous topics. Derivatives of carbonic acid. This is called carbonic acid. It's a carbonyl with two OH groups. This compound is not stable. This compound will decompose into water and CO2. It's an equilibrium, but the equilibrium shifts to the right with escape of CO2 gas. Unless it's a closed container, CO2 is going to escape and the equilibrium will be driven to the right. Okay? A can of Coke has carbonic acid in it, but when you open it up, the CO2 escapes and the carbonic acid will diminish. The equilibrium goes to the right, CO2 escapes. And so as your Coca-Cola ages, it will get less acidic. This is slightly acidic. Okay, it's a carboxylic acid. Monoacid derivatives are also not stable. Not stable. This will decompose to ammonia and CO2. Okay. Ultimately, anytime you can, we can show this a couple of ways. Maybe we could just make pi bond here and kick this off, and that would give what? Instead, let's go the other way because we're kicking off. We want to make CO2. Make CO2. So these electrons would come here and kick the nitrogen off. Anytime you make pi bond kick off leaving group, easy to do. Okay. And that would give what? That would give this here plus what? NH2 minus. And then these electrons could just take the H, and what does that give? Well, there you go, NH3 plus CO2. So we can envision a mechanism like that. One molecule breaking into two, driven by entropy. Anytime you make the pi bond kick off a leaving group, easy to do. Okay. Now diesters are stable. Ester on both sides. This is called diethyl carbonate. That's a stable liquid compound. The dichloride is stable, believe it or not. Questions?
On the example that you showed, do you know, like, do you have to look at the products in order to determine which electrons are supposed to move in? Like how you had started with the electrons on the nitrogen, but when you look at the products, you realize that it had to be the CO2. Is that the only way that you can know?
Yeah, I mean, you just kind of know where you're going. I don't know, I mean, it seems kind of intuitive that maybe the oxygen's a better leaving group. So these can come in and kick off the oxygen, and you lose water, essentially, in some type of nitrogen, carbon, oxygen thing. And we just know that doesn't happen, so yeah. So again, that may be more intuitive, and that's kind of what I did to begin with, but then, oh no, we need to make CO2, because this is what is known to happen. So for some reason Mother Nature gave us that way. It's also, there's possibly acid-base chemistry here. I don't think you're going to self-protonate this nitrogen with the carboxylic acid. But it's probably maybe hydrogen bonding. It may be a touch more complex than just a unimolecular mechanism. There's lots of hydrogen bonding going on there that can maybe make it go this direction. Question?
Since that diesters are stable, does that include asymmetrical diesters?
Yeah, that would include asymmetrical. That's a carbonate is symmetrical. Yeah. So the dichloride is called phosgene. It is a gas. It's very electrophilic, very reactive, and it actually has been used as a chemical weapon in World War I, back when they first started using poisonous gases. Bad stuff. Because this carbon here is very electrophilic, and nucleophiles all in your body, in your lungs, including in water, will react with phosgene. And you're going to generate HCl typically. If you react phosgene with water, you're going to get HCl. By water adding to the carbonyl, chloride leaving, then the Cl- will come back and pick up an H. And so not only could that react directly with proteins in your body or enzymes or various things, it can also generate HCl in your body. And if you generate HCl in your lungs or in your eyes, then you got problems there as well. If you ever watch some of the James Bond movies, sometimes one of the movies, I know they alluded to it, some of the bad guys put some phosgene in a cave, gas to, and then somebody says, "Quick, phosgene, get out." Okay, the diamine is also stable. Anybody know the name of that diamine? This is urea. You've seen urea in biology courses? Okay, that's urea. Okay. It's a byproduct in a lot of life forms to excrete urea as a way to get rid of nitrogen byproducts in your body, like ammonia. Okay. The ammonia becomes bonded to a carbonyl in biochemical processes. Mixed derivatives are stable. This is called ethyl carbamate. So it's like an amide on one side and an ester on the other. But the acids are not. Okay? You start having esters, R groups here, stable, or two nitrogens are stable. Salts of carbonic acid are stable. The monosodium salt, right? So if that was H, it'd be carbonic acid, not stable. Monosodium salt is stable. It's called, what is it? NaHCO3. Okay? That's sodium bicarbonate. Or the disodium salt. That would be called sodium carbonate. Okay? So both of these are stable. All right? But if you take either one of these and put them in acid, what are you going to get? Well, this anion will just protonate, and when that protonates, what do you get? Carbonic acid, but that's not stable. So what does it become? CO2 plus water. But the CO2 is a gas, and it will come bubbling up and frothing maybe. Okay? And in third grade, you took baking soda and you put it in a mound and you added some acetic acid vinegar, and it would, you made a volcano. Right? CO2 coming out. But did you know that between here and here was carbonic acid, which quickly gives CO2. Another topic, condensation polymers. If you look at this amino acid, it's not an alpha amino acid, but it's an omega amino acid. If you dehydrate onto the carbonyl, you're going to get a cyclic amide called a lactam. Okay, we can do that. But we can also make a polymer here. This would be a monomer by cyclization. You can also make a polymer chain. And that would be where the amine condensing with the carbonyl. Yeah? And if you just did that once with different molecules, you would get what? If another amine condensed here, we would get an amide, yeah? And then that would be what? That would be the amine, and it would have boom, boom, boom. I'll lose track of carbons. One, two, three, four, five, six. 1, 2, 3, 4, 5. Yeah? That is just where two molecules came together by condensation at the carbonyl. Okay? But we can keep going. What if I had an amine condensed here? We would then have nitrogen, and then we would have them in a carboxylic acid. And then we could keep going. We could have nitrogen, and then on the end we'd have carboxylic acid. Okay? Somebody stop me. What do you have? It can just keep going and going and going because each end has double reactivity, or each molecule has double reactivity. Repeating unit here, well, right here, NH2 carbonyl. That's what I showed right here. Repeating unit, on and on and on. And that is known as nylon. Okay? It is a condensation polymer. Because we're losing H2O. Question?
Could one of the nitrogens bond to another nitrogen, or can the nitrogen only bond to the carbon double bond?
How would a nitrogen bind to a nitrogen?
What reaction have we ever done with a nitrogen binding to a nitrogen? I don't think we've done one, but
We've done plenty of nucleophiles bonding to carbonyls. Nucleophile bonding to carbonyl, some type of leaving group. I don't know of any reaction, certainly that you would know, to make nitrogen bonds. Okay, that is going to require some type of acyl substitution. If we don't have, acyl activation. If we don't have any activation, we could envision just this acting as a base, taking the H. If that took the H, it kind of looks like game over because, like we said, this is very unreactive towards NAS chemistry. Okay? Here's some other condensation polymers. Kevlar, which is used to create so-called bulletproof vest. Okay, these condensation polymers typically are amides coming from condensation, yeah? Proteins in your body come from alpha amino acids. Well, we just looked at amino acid. It was just the amine was further away from the carboxylic acid. The first carbon is the alpha carbon. Second one from the carbonyl. The second one is the beta carbon. And the third one is the gamma carbon. And your OH group is on the gamma carbon. Okay? That's why it's called gamma decalactone, because that's where the OH group was before it cyclized and became the lactone. Make sense? But these things can undergo condensation, polymerization to give proteins and peptides, etc. Okay? Shown here. Okay, any questions about chemistry of acid derivatives? Everybody get a handout today from the tan and the white? What? Okay, simple additions to carbonyl. We're moving on from acid derivative chemistry. Everybody good with acid derivative chemistry? I don't believe it for a second. But we're going to move on. Okay? You guys seem to have not be working problems or asking questions. I'm concerned. I'm not going to basically stand up here when you're not prepared and ask you questions, etc. Okay? I'll move us to the material. It's hard to respond when you don't have questions and you don't seem to be prepared. I'm not looking at everybody, but I see a lot of people who are not prepared for class. I haven't looked at every single person. But enough of that, okay? At some point we will have quizzes, tests, and final grades, okay? You're here for a purpose, I think. All right. You plan to take biochem? Okay, all right. Reaction of carbonyl compounds. With hydride reagents, Grignards, okay. Looking at simple additions here, okay. And I'm going to present this as basically different reactions and products here, and the chemistry that's going on. And we're moving to aldehyde ketone chemistry, okay. But we still have carbonyls. And we're going to see new reagents. Some new. We saw sodium borohydride in organic 1. What was that a source of? Sodium borohydride was a source of what? What was its reactivity? What? I can't hear. Sounds like you're saying hydration. No, you would hydration. You would use water to hydrate something. We use it as the second step in the oxymercuration, followed by overall hydration of alkene, but sodium borohydride doesn't hydrate. Sodium borohydride is an H- source, right? Both of these are. And we have H-, and these electrons add to carbonyl, electrons up, and that would give what?
nucleophilic addition to carbonyl. And what's going to happen next?
The electrons come back down and kick off the
And kick off.
reaction.
Why would they kick off the methyl?
But they kick off the phenol.
As I know you're aware of, note that a standard carbon, such as a methyl or H, will not be a leaving group in an addition elimination reaction. So, what's going to leave? The what?
The ring,
I didn't hear you.
the phenol.
Phenyl? Yeah. No, it's not going to leave. It's not going to leave either.
It's certainly not a methyl or H. It won't leave either. Somebody over here say something? That's it. Game over. There's no LG here. Okay? No LG. Aldehydes and ketones don't have leaving groups. At least not unless it's some very strange, unique reaction. Okay? A plain carbon group, and including a phenyl, is not going to leave. At least not easily, and for basically us, no. Game over. The only thing you can do here is put on protons, workup. Okay? Now, a lot of times you use like maybe ethanol, a protic solvent. And if you include a protic solvent, it can supply the proton. And what will your product be? An alcohol. Now where's this H at now? Right here. I just didn't draw it in because it's a line bond structure. It's got a new H here, right? Yeah. Now essentially, two H's have been added. So what type of reaction is this when we add H's? That would be a reduction. Sodium borohydride. Remember the structure of sodium borohydride? Boron has 4 H's. Minus charge. Sodium ion. And because the boron is negative, it's like, hey H, you and your electrons go. And so these electrons move in the H and 2 electrons. It's like H minus. Like H minus starts. H minus nucleophile. Okay? But that H minus will attack the carbonyl. Electrons up. Just sits there. It can take proton from ethanol. Lithium aluminum hydride. Instead of boron, it's aluminum. Aluminum is right below boron in the periodic table. And here, lithium ion is most common as a counter ion. Okay? Different with LAH though, which do you think is more reactive? Let's draw LAH. Okay? And this is often abbreviated as LAH. Which one is a more reactive hydride source? A stronger hydride source? Which central atom is matter? Which one hates being an anion the most? Why boron? Larger atom, but able to handle the charge. That's a good argument. It's actually the wrong argument though. Which one's more electronegative? It's actually a very good argument, but it's counter. It just doesn't give you the right answer. Okay, and a lot of times you make good arguments that are just wrong, and then you have to figure out why. Well, why is it wrong here but not wrong over there? But the argument that is right here is, which one's more electronegative, aluminum or boron? Boron's more electronegative. Thus, boron likes minus more relative to aluminum. Okay? Now, there could be other arguments there, but that argument certainly fits the experimental observation that LAH is more reactive. And I say, well, this aluminum must be matter, and it's like, hey H, you and your electrons really got to go. Because of that, LAH, you don't want any protic solvent. With sodium borohydride, you can use protic solvents, but with LAH, you can't. Because if you got a protic solvent, like ethanol, how could these two react? These take H, and what are you producing here? H2 gas, which is flammable. Okay? You take LAH, put it in some ethanol, it's going to start burning and igniting and blowing up on you. It's producing hydrogen gas, and then that will ignite. Okay? Sodium borohydride won't react that way with alcohols. All right? Which suggests it's less reactive. And then we try to explain why this may be less reactive. Okay, so they're both hydride sources. If you use LAH, you usually need to come in, well, you got to have to. You supply the H with workup after the reaction, okay? Such as aqueous workup.
Yes.
So does that explain, like, when we use the NaBH4 in lab for the safety precautions, it said that if it was combined with water, it would produce flammable gas? Is that the explanation behind it?
Yes. But it reacts very slowly with water. But it will. If you put it in there and start heating on it, you can get it to do the reaction with water. Yeah. LAH, you don't have to do anything. You better run if you add LAH to water. It's going to do it very quick, make hydrogen, it's going to be so much heat, it's going to ignite. Yeah. LAH is actually a little bit dangerous to handle. Sodium borohydride is much less reactive, but theoretically, and you can make it react with water like that. Okay. Basically, it's H minus, and H minus will react with H plus. And H plus can come from an acid, but it can also come from a protic. Something that's protic, because, I mean, ethanol is a very weak acid. It's all relative. If you got a strong enough base, ethanol could be an acid. Or methanol, any alcohol. Okay, so we had product that looked like this. That is a reduction because we've added H's. And we call these reducing agents. Question on the right, how would you convert this back to this? First off, what type of reaction would that be? Oxidation. What reagent would do that? Ever oxidized alcohols to carbonyl compounds? Yes, test one. What did we use? One of the big three. Yes. So this becomes a cycle, okay? We can reduce carbonyl compounds with something like LAH, etc. And we can oxidize them back. That's a redox cycle. If you look over here, see the same type of thing. This is very common in biological processes. Okay, for example, estradiol. Estradiol has an alcohol here. If we oxidize it, we get the ketone, which is called estrone. But we can go that way. And if you reduce estrone, if you reduce the carbonyl of estrone, what will you get? Okay, estradiol. All right? Because there is another OH here, so it's called a diol. All right? Now, your body doesn't use sodium borohydride or LAH. Your body uses other reducing enzymes. But you see the cycle here. And you need to know the functional group conversion. Alcohols to aldehydes or ketones. And the next page shows some information about NADH, which is your body's hydride source. Okay? Please take a look. Can you show the product of the next two reactions? Again, when we do these reactions, a lot of times aqueous workup is sort of implied. Think mechanistically. Once you get good, you can sort of know, hey, I'm reducing my aldehyde to what? Well, it's going to be an alcohol. But instead of just memorizing that, you just work mechanistically and, okay, there's your product. Okay? What do we got here? H minus. These electrons add to carbonyl, electrons up. What do we get? H. Now 2 H's here, electrons up. Yeah, that's just nucleophilic addition to carbonyl. What now? Nothing. Game over. All you can do is what? Work up. Okay? Add some water. That'll put the proton on, or acid. Or if you're doing sodium borohydride, you can use a protic solvent, and it will put the proton on during the reaction. But essentially this becomes what? There you go. There's your product. Is it okay if I draw the oxygen down instead of pointed up? Yeah? 1, 2, 3, 4 with an OH. 1, 2, 3, 4 with an OH. That carbon has 2 H's. Well, they're still there. This carbon got 2 H's, right? So I can put it in a kind of a straight line bond structure and still be the product. Okay, you'll be able to see that. So the aldehyde got reduced to a alcohol. Happens to be a primary alcohol. Now some books will tell you, okay, memorize that an aldehyde gets reduced to a primary alcohol. Don't memorize that. Just show your product. If you want to then realize it's a primary alcohol, you can then do that later. But please don't memorize such. Okay? Think mechanistically. You show your product. How about the third one? Okay? It's the same reactant. What do we got here? Okay? Show the product here. We didn't answer this question over here. Think about that. How would you convert that alcohol back to this aldehyde? Anybody got that real quick? PCC. Yeah. Not one of the big three. Big three would convert it to a carboxylic acid. Okay? All right. Anybody got the product down here? About this alcohol here? Yeah? It's the same reaction as above, except above the nucleophile was what? H minus? Down here it's what? It's phenyl minus. Same reaction otherwise. And so, instead of having 2 H's on this carbon, we got 1 H and a phenyl. For this product, will it be R or S? Because that's a chiral carbon. Will it be R or S? Okay, I'll let you think about that. We need to be able to go backwards. Synthesis. How would you synthesize this compound from carbonyl compounds? Please read the directions and give that a try. Synthesis, going backwards. Okay? Okay, guys, see some of you in lab at 2:30 today. Okay, we can deal with these issues. And I'll likely send out an email, but I'll have to be posting lectures, handwritten lectures, video recorded. I'll have to be posting those. Okay? If we would have been here on Monday, we would have had a quiz on Monday.